Hello everyone. My name is Sigurd Aguiar from the RADNEXT Project Management Office, and I'm delighted to welcome you to today's webinar hosted by RADNEXT. So thank you all for joining. So I will start by giving you an overview of the RADNEXT project and what it stands for. So RADNEXT is a European initiative that provides free of cost access to state-of-the-art irradiation facilities for researchers and users around the world. So this is a unique opportunity allowing for radiation testing across a broad spectrum of scientific and technological studies, not only space applications, but also medical applications, high energy physics, and many other ground level applications. As the project is approaching its final year, we are very proud to share that we reached over about 4,000 hours of beam time already provided to users, and we have assigned already over 5,000. So our main goal is to reach around 6,000 by the end of the project, which is beginning of next year. If you still want to have, if you still want to take advantage of this free of course access to one of our facilities, the final call for proposals is scheduled for September this year. So the last call is September 2025. So prepare your proposals and submit on time during the month of September. Looking beyond 2026, after the end of the project, we are already planning a follow-up initiative, RADNEXT 2030, which will continue to support the advancement of radiation testing technologies and also open up new opportunities for researchers worldwide. So we are very excited to see how RADNEXT will evolve and continue to contribute to this scientific community in the coming years. So if you don't want to miss out on any opportunity or activity related to RADNEXT, I would recommend you, if you haven't already, to follow us on LinkedIn, because we have a very active account where we regularly post about the call for proposals, the events we organize, and many other activities. So it is a great way to stay up to date with everything happening within RADNEXT, but also with the wider radiation testing community. So don't miss out and follow us on LinkedIn. We also maintain a open access repository on Zenodo with many documents related to the project, including reports, preprints, papers, presentations, and many other different documents. And as you can see in the right side, for example, we have a transnational access summary report that for each beam time provided, the user needs to submit this report, and we upload it to Zenodo. So this is a very useful and excellent resource for anyone wanting to explore what have been done in the project and different types of research that we have supported over the past few years. And not to extend it longer, the introduction, so we're here for the RADNEXT webinar series on radiation facilities. For the past month, we had some other webinars on heavy ions facilities, and today is not different. We have another heavy ion facility coordinator here, Dr. Steve Lydia. We are very happy to have you here and learn more about this new facility for FSEE testing. So I will just briefly read your bio so everyone is aware about your nice curriculum. So David, Dr. Steve Lydia is a senior scientist at the facility for Rare Isotope Beams at the Michigan State University, and a professor in the departments of physics and astronomy, and also electrical and computer engineering. He specializes in accelerator physics and engineering, leading a technical department in beam instrumentation and measurements. Since 2001, he has been the principal investigator and manager of the FRIB single event effects beamline, and also principal investigator for the Key 500 SE facility that we're going to learn more about today. So as a reminder, this webinar is recorded and will be uploaded on our YouTube channel. We will have the Q&A session at the end, which will not be recorded, but feel free to leave any question during the presentation on the chat that we will bring up by the end of the presentation. So with that, I'm happy to hand over to our expert, Dr. Steve Lidia.
Thank you, Igor. Thank you very much. Okay, so
You should
all
be
right,
able to share now.
yes. Let's see. So that's all right, and we're still loaded and ready to go. Good. Well, good morning from me, and good afternoon to all of you. I'm Steve Leidy, and I want to talk to you about the facility developments at Michigan State University that we've been pursuing for the last few years in the areas of heavy ion-based single event effects and radiation effects testing. There we go. So just kind of the outline of the talk. I'll talk about how we've established a test facility here at Michigan State University, and then how we've grown that facility based on user needs and as well as some of the kind of the unique capabilities of a linac-based system. And then I'll talk about how we're extending our capacity and reach into other areas. So shown here is a photograph of the facility for rare isotope beams. This is located centrally on the Michigan State campus, which is a large campus. You see in the lower right the office buildings on the office complex. At the rear in this kind of L or pseudo L-shaped section is the facility. Well, is the superconducting RF linac, which is our new driver for we started off with nuclear physics, and now we've added radiation effect studies. Experimental beam lines are kind of shown here, kind of in the middle between the office and the linac driver. And then also on the other side is our basically our cryo module assembly building, where we now have an additional world-class facility in assembling cryo modules, testing cavities, and developing the infrastructure we need for the linac. So in terms of a brief history, so prior to the installation and implementation of a linac-based driver for nuclear physics and these types of studies, we were a coupled cyclotron facility, and before that, a single cyclotron facility. So the last incarnation of our nuclear physics program used a tandem K500 cyclotron driven by an ECR source as an injector to a K1200 cyclotron to generate ions up to about 200 MeV per nucleon. And then that would and these ions then go to a target system and a fragment separator, and then onto experiments. For SEE testing, we had a beamline, or a portion of a beamline, where a small test stand was developed, which has a PPAC detector for essentially intensity, beam distribution, and rate. A translation stage for mounting boards or other DUTs, and it's a fairly rudimentary but workable system. And so this was circa 2004, so about 21 years ago. And we delivered a handful of beams, looks like 4 beams or so, in the energy ranges up to almost 150 MeV per U. This was lightly used, I'll put it that way. I think after this development, most users in the U.S. were again using facilities, a single cyclotron-based facility at Texas A&M, TAMU facility, as well as the NASA's Space Radiation Laboratory at Brookhaven National Laboratory, NSRL. And so this lay dormant for a few years until I guess it was 2020, so 5 years ago, where we were approached to develop capabilities based on the linac system with the brand new linac. And so to kind of show you the capabilities of the facility for our isotope beams and our linac, here's kind of a view. This is over several levels. In our sub-basement is the linac facility itself. As you can see, the linac is folded twice, so it looks like a paperclip, where there is a low energy beam line in the middle, or low energy accelerator in the middle, two folding segments, and then a long linac segment, which we call LS2, and then the final linac segment, LS3, which is used to accelerate our ions up to 200 MeV per nucleon. And we've demonstrated 200 MeV per nucleon with uranium. I think uranium 76 plus. Following the LINAC, there is a target system, and then there's the rest of the infrastructure for the nuclear physics program. As I mentioned, we were approached to develop an SEE test facility, and so that's here at the end of the first LINAC segment. You see this little spur, kind of in a greenish color, coming off. And that was our initial installation. So this is the facility that we use. It's located in the LINAC tunnel itself, which creates some interesting logistics and management of getting users in and out on a frequent basis while the LINAC is in operation or in a standby mode. And also the other thing to realize is this LINAC system is based for essentially, it's an intensity frontier machine. We are currently delivering 20 kilowatts of heavy ions to the target facility. The ultimate goal is 400 kilowatts. So it's overkill for this type of testing, for radiation effects testing, where we need, microwatts of beam power. And so one of the first things that we have to do is attenuate the beam fairly strongly at the front end section. So to show you what the actual beam line looks like, so here's that spur line at the end of the LINAC segment 1. There are the red magnets or dipoles to direct the beam onto this beam line, and then we have a standard set of quadrupoles, and then the beam transforming section. So this is a well-studied type of optics transform where we use basically large aperture quadrupoles and octopoles. The blue magnets are octopoles to essentially convert a double Gaussian beam into a uniform beam with some high intensity ears that are then chopped off at a collimating section here, a little bit downstream, and then delivered at the end of the beam line to the user. So the user station is at the far right in this picture. Based on the requirements from the community, these are the parameters that we were required to produce, both at thresholds as well as kind of aspirational values. So the LET in silicon that we provide is less than 1 and greater than 80. So 0.7 to 82 is appropriate for the ion species we're using. Fluxes of basically 0 to about 10 to the 6 ions per square centimeter per second, with kinetic energies up to about 44 or low 40s megavolts per nucleon. That's for that would be for our oxygen beams. Our heavier beams are more in the kind of 15 to 25 MeV per nucleon range. The beam diameter only up to about 2.5 centimeters in diameter, so it's a decent format. It's a size of the beam that will cover most components on an electronics board, but it won't do the entire board. So there's a development plan that we have to increase the beam size that we deliver to the boards up to kind of the 50 millimeters or sorry, 50 centimeters size. So that's a very large beam for us. And then there's some other parameters in terms of the beam uniformity, the energy purity, the species purity, as well as the kind of the time and the allowable time structure on the flux that we deliver, and all of these have been delivered at the end of the project. So the beam line itself is kind of shown here schematically. You saw a photo already. So the entrance from the LINAC is at the kind of the bottom right here. The the quad octopole transformation requires that we actually have to degrade the beam quality a little bit. We pass it through a scattering foil, and that just increases the emittance somewhat, so that it can go through this transform and create a much more uniform beam. Um, that adds a little bit of energy degradation, which is then accounted for in our dosimetry and final energy delivery. A couple of Faraday cups are of course included for making intensity measurements. This first Faraday cup is a beam stop, and that was initially used as our beam shutter by the user. So they would insert and retract a Faraday cup essentially for starting and stopping the beam. We've since moved on from that, but that was the initial implementation. The last, well, there's the final window cross here on the vacuum chamber, which basically just has a window, vacuum gauges, and a fast connect and a connection to a fast acting gate valve, which is shown right here. Haven't had an incident yet, but it's built in. And then our final dosimetry is in this cross about 3 meters before the window, where you see this four jaw on the upstream cross, a four jaw collimator, which is used for final beam shaping and aperturing, followed by a viewer and a Faraday cup. We have at the exit, kind of, you look down at the lower left, at the exit of the window, we have an in-air viewer, as well as a lithium drifted silicon detector behind a light block, a small thin mylar foil. So we have a way of measuring very small fluxes at the exit in air, approximately where the DUT would be. And so that's our instrumentation package. I mean, we also have the entire linac, of course, with all of its diagnostics, as well as the front end, which is providing us, additional information that we need to generate the dosimetry information for users. The end station again, kind of, looks like this. The window, or the nozzle, the hose where the ions come out, is for our users. A set of targeting lasers for alignment purposes. And then we have a number of cameras that are kind of mounted around for monitoring the position and the overlap of the lasers with the DUTs during testing. Here in North America and the United States, there are several long existing test facilities. Texas A&M with its K500 cyclotron-based system, as well as Berkeley Labs with its 88-inch cyclotron. Those are, again, well-established and well-used facilities, and so not to be different or reinvent the wheel. We've used essentially the same type of mounting plates. We tried to make it as the interface for the users as seamless between the different facilities as possible. And so we've used similar designs. One of the things that we had to do, however, was look for a new vacuum window material. Existing facilities, a lot of facilities, or at least Texas A&M, in the low energy regime for heavy ions, where you're really concerned about the energy loss of especially the heavier ions going through the window, and so that we need thin materials. They were using Aramika foils. There's also Havara non-magnetic alloy. However, Aramika seems to be the preferred type of window material, but it's no longer available on the market. So Texas A&M, I believe they've got a nice stack, and I didn't want to necessarily dip into their stack by asking. So we developed a new window material. Well, we didn't develop the material, but we adopted polyethylene naphthalate PEN, which is a kind of a higher temperature type of polymer, resin-like material. And we initially metallized both sides. Here's the air side as well as the window side, or the vacuum side, where we put a small amount of metallization. The intent there was an initial try at developing essentially a diagnostic, just to try to read back the charge that was exiting the window as a means of adding additional diagnostics for dosimetry. It didn't work. It was too noisy. And honestly, after a few months of operation, the metallization was gone and it sputtered off. So I'm glad we weren't depending on that, but it was there initially. We went through some trials with this material before installing it. So here's essentially a vacuum test that we did on the bench. We also added a heat gun element to it, so you can see the temperature, and I believe that's in Celsius, that we were able to drive the window to with measured by a thermocouple. You kind of see on the edge over here. So it's a fairly robust material, and we've in the last, I guess, 3 years of operation, we're only on our second window. The first window we just removed. Um, uh, we removed after 1 year of operation without any issues. We were just getting a little nervous. So we took it out. It's fine. And the window number 2 has now been in for 2 years, and it's due to come out this summer. Our control room, again, it's kind of shown here, just a picture of the control room. So this, however, as I mentioned, our facility is in essentially the sub-basement, under a lot of shielding. So it's 2 floors up to get to the control room. So it's a reasonable distance for the users. It takes about 2 minutes to go from here down to the beamline where they can access their devices. So that's one issue that we have to deal with getting access, and we try to make that as efficient as possible. However, there's also a long cable length. It's on the order of several hundred feet. So if the users want to run their own cables, we do have a designated cable tray for it, but it's a long cable length. And so we provided, kind of shown here, as a patch panel underneath these monitors, a patch panel for Ethernet cables, as well as some analog cables, coax, as well as some multi-pin cables if they want to use those. We haven't had great luck with getting low-level analog signals from device testing up over those analog cables, but users with this energy scale facility, where we're not creating a lot of background radiation, they can site their instrumentation right next to the beamline, right next to the devices, and then utilize these Ethernet cables to talk to their instrumentation, and then using keyboard, mouse, video links, kind of shown here. We can pipe those into these monitors, or they can use laptops or other interfaces. Background, kind of a monitoring screen is shown here, which, again, shows those images from those cameras, as well as, kind of beam information, and process information during the testing. You can kind of see the time history of the flux and the fluence as it develops. The user controls there's kind of shown here over on the side, is done through a touchscreen panel. So this is a panel view system. We've developed that in-house. And so there is one of these panel view touchscreen interfaces in the control room, and another one resides next to the beamline, so that the users can move the stage around. They can generate preset values for stage positions. They can control the lasers. They can calibrate the air gap with a Z laser. And then they can start and stop the runs as necessary, and then generate reports all through the touchscreen panel. Our initial complement of beams are shown here. So again, this provided us a set of LETs from less than 1 up to over 80. So oxygen through bismuth are the beams that we provide. Again, and with these types of fluxes. So the fluxes, the maximum flux for the light ions is about 10 to the 7 particles per second per square centimeter. For the heavier ions, it gets down to about 2 to the 5. And that's just due to essentially overly conservative estimates for heating on the window. So these flux numbers, the average flux numbers are based on some calculations that we did on background heating of that window material, assuming a temperature rise of, I have to remember exactly what, but something on the order of about 25 or 30 degrees Celsius maximum. Um, we've we we found kind of empirically that we can relax that a bit. I mean, I think our safety margins were more than a factor of 10, so we are able to relax that a bit. But those are also relatively reasonable values for our users to use for fluxes. So as I was mentioning, some of our instrumentation. So there's those four-jaw collimators that we use for the final beam shaping and collimation. They're actually isolated, and we read those back onto sensitive picoammeters as our way of measuring and when we cross calibrate those against Faraday cups to the beam flux. And so this is our way of essentially of monitoring in real time through that signal what the delivered beam flux is. A Faraday cup and viewer are also used for tuning and of the beam spot prior to delivery. Scintillator, infrared camera, silicon detector, et cetera, in air for final beam delivery. So we use these plus the upstream beam position monitors in the linac for time of flight measurements. We have a number of diagnostic elements next to the ion sources at the far end, the other end of the linac system, which is used for performing our charge state distributions, so that we know which mass and charge state that we're sending down the line. And so, anyways, we utilize this whole package and suite of instrumentation to verify our flux, our energy spread, beam purity, the beam energy, as well as the beam flux and intensity. So as you might recall, this quad octopole beam transformer does an interesting thing with nonlinear optics. So in particular, it takes, if tuned correctly, it takes a Gaussian beam in both horizontal and vertical dimensions, expands it, moves intensity out to the sides, and can generate a relatively flat profile in the center with these kind of large amplitude ears at the end. And so one of our jobs then, and you can kind of see the ears here in the vertical plane in the in this image. And this is the track simulation, not actual data, but the real data looks similar, of course. But this is how we do the tuning. So we will now use those collimators to block various portions of the beam. And you kind of see by doing that, we've now generated essentially a square uniform distribution beam profile that is then used to irradiate and expose the boards and the elements and the components. However, as you can kind of see here, these slits, these capture about 90 to 95% of the total beam intensity. So not to want to throw away that information or that opportunity, we've connected those to ConELS. They make this nice set of instruments that we use fairly ubiquitously through the entire linac, picoammeters and these tetrams. It's a 4-channel picoammeter that gets us down into essentially the pico or the femtoamp regime for measurements. And so we use these instruments for measuring the amount of charge that's collected on the slits themselves as our background monitor for beam intensity. The dosimetry then looks similar to this during basically a set of exposures. This is a little bit of synthetic data, but you kind of get the picture. The flux in real time is then kind of shown here on the red curve. This is a time scale of about 20 minutes, and so each of these runs here is about 100 seconds. A cross calibration of the four-jaw against the Faraday cup is kind of shown here, and then the integrated fluence starts from 0 and goes to whatever maximum. This is the type of process data that the users can see. So they can see in real time if there's any drift, any burps, any interruptions in the delivery of beam flux. And then all of this information at the end of a run is captured in a run report. This is interesting because this run report was our first example of a run report for the users, and it captures essentially all of the flux and the delivery information. We've since expanded this with many other parameters that are then delivered to the users. It's about twice or three times as long as this now. A lot, and some of that is based on our pulse beam delivery. But this has been delivered on demand by the users when they press, send the run report. We send a batch of all of the runs collected to that point in a text file, as well as a MATLAB file, which incorporates some of the waveform information, in particular of basically the run by run flux versus time. And so they have that for further analysis of the performance and behavior of their parts. During our initial tests and acceptance tests by our funding agency, two teams, one from Jet Propulsion Laboratory and the other from University of Tennessee at Chattanooga, came and did some testing with us. So this is essentially showing the results of an SRAM test as well as an op-amp test from those two groups. In this, on the left side, the MSU, the FSEE beamline is kind of shown here with these green triangles. And on the right side, we are the blue, essentially the blue stars there on cross-section plots. And once we started seeing this, Greg Allen's nice quote was, "You're in the family." So that was a nice bit of acceptance from a couple of testing teams. Now this was essentially just a few little spot tests, but that verified the operation of the facility as well as the dosimetry that we're providing. Okay, so that got us going. And that was that's about 3 years ago now. So we started now with a list of users. We had one company, Texas Instruments, work with us very extensively, trying to essentially help us to develop the facility, develop our capabilities, our user interfaces, and make things essentially just much more convenient for the users to use. But once we started, they came and started developing a long list of needed improvements, just to make things more efficient on their end, to add capabilities and fill in some holes as they would see it. So we took that, we took it seriously, and we appreciate all of the input that we've received from all the various users, and that's led us to develop some interesting capabilities, both in terms of SEE facilities as well as in operations of superconducting RF linacs that we've had to develop kind of in response to this mode of operation, which is a little bit different than most SRF linacs have to deal with. So I'll go through some of that. First thing was we added some new species. So we had a hole in our LET at around 40. So we added gold as a species. Now the ECR sources, our plasma sources that we use to drive the linac, were, as you might imagine, not well optimized for this type of work as they might be on a cyclotron-based system, or any system which is essentially developed just to generate and deliver a single ion species over some significant amount of time, whether it's hours or days or weeks. Here we want to be able to change the species, at the drop of a hat, and definitely within a few hours. And so we're constantly changing beam species, and so we have to have them available. Cyclotron-based systems use the concept of a cocktail where you have a number of ions loaded into a plasma chamber, The cyclotron itself is an excellent mass filter at a given energy. And so you can very quickly switch between different ion species coming out of a cyclotron. In a linac, it's a little bit more difficult. Any ion with the same or within a small range of charge to mass is going to get accelerated down the line. So we have to do all of our um, um, charge and mass state differentiation at the front end, so right at the exit of the ECR, and that makes things a little bit more difficult. But it's workable, and so we've been able to develop now a set of beams that we can deliver to the users to basically fill in all of the gaps and good coverage of LET from basically 0.1 up to 100. And still only using up to bismuth. We do have the capability of running uranium, should anyone so desire it, for an LET of about 120. That's, I guess, if you really want to destroy a part in a short amount of time. All right, other functional improvements. So we didn't initially have this, what we're calling a laser ruler, or it's a vertically oriented visible laser system that you can use to calibrate the position of a part, or basically a DUT under test from the window. So you calibrate the air drift. You know, different parts, different boards, they have different locations in space, and so we have to be able to calibrate that. And so one of the first things was implementing that quote unquote laser ruler, and then having essentially a graphical feedback system so so the users can tune somewhat in real time. And I'll talk about that in a minute. Also a degrader wheel. So we didn't have any other degraders initially. We had a cap that you could attach to the exit window, and stick some shimming material in there for different degraders. But that's all, you can only do that one at a time, and then have to go down and change it. And so we implemented a wheel, and then updated the user interface and the status screens to provide a lot more information at the right times for them. So the degrader wheel is shown here. This was essentially an optical filter wheel. Very easy implementation. We were just able to to buy that online. We are also then able to incorporate the controls within our EPIC system, so our main control system. So it's integrated seamlessly with the kind of the accelerator and the beamline and the user controls. And then also integrated into our dosimetry system. So the users can make the wheel turn, put in different thicknesses of materials or no material whatsoever, and the dosimetry, the LET and range automatically update based on all available information of the beam type and energies, for instance. We developed a large database. So this was looking now at our set of ions with their particular energies that we deliver. So using a finite number of ion and linac tunes, and then incorporating different degrading materials, those scattering foils I mentioned earlier, different positions of the degraders, and then assuming initially that the beams were going to be impingent upon silicon as our base material. We've since updated that. We developed a database of different, which captures different air drift lengths, all of the different kind of finite material parameters, and then different essentially depths in the silicon. And developed, kind of an energy and a range and an energy deposition type of profile in this database. The database then allows us to construct a set of controls for the users, and that's kind of shown here, where again the users can select maybe a different air gap, a degrading material or thickness from that wheel. And then this graphical readback then updates. So the red line shows the range based on incidence at the surface of silicon as a function of the air gap distance. And so as they move the stage in and out towards the window, this green line here then translates across this page, and where it intersects would show you the range as well as the surface LET in that material. We've since updated this, so we're not talking about just silicon. We've got a host of other materials. I think the list is up to about 12 or 15 materials right now that would be used as input into this readback. As the degrader material or the air gap or however is changed, this updates immediately. And so the users can actually see this on a secondary screen down at the beamline and then up in the user control room. And so they can do fine tuning of where of what the gap is so they can fine tune the LET at the surface. And the last improvement we've made now is to show the penetration and the LET through materials so that they can actually use this type of control to select where their sensitive region may be as a function of depth and put the Bragg peak there or in front of or behind it. And so this was a very useful tool for the users in real time. Okay, so I mentioned that the test facility is located in the linac tunnel, and that means that the users are in the same space. There's no other additional shielding between them and the linac cavities, the linac cryo modules. So we have to make that area safe for the users to enter and to access. There were two ways that we considered. One was, incorporating active monitoring with X-ray monitors, maybe at various places and definitely around where the users would be working, such that if they detected a cavity breakdown event, they would cut the power to that cavity, precipitously. We decided not to go that route. The route we decided to go to, which was we removed the risk altogether, is just to lower the cavity amplitudes, lower the voltages in all of the cavities, in this case, the first linac segment only, but lower all of those amplitudes to zero and remove any type of X-ray generation mechanism. Allow the users to access the beamline, make any changes to their parts or their instrumentation, and then exit. And then once they've exited the area, then we have permission to turn the cavities back on. And so that's what we do. Now, initially, an SRF cavity, as you might imagine, doesn't like to be turned on and off very frequently. It doesn't like change. It likes to just hit its value, hit its amplitude, hit its phase, and stay there. And so this is a somewhat unnatural position for the cavities to be in. But we developed a set of excitation and tuning, kind of shown here, where we start from kind of essentially a self-excited mode, and then quickly go into an amplitude-dependent mode. That was our initial process. Our last iteration is we bypass the self-excited mode altogether, and we basically move the piezo tuners for the cavities to their nominal final amplitude position as we turn the cavities on. And so it's a controlled process. It's a well-studied process at this point, and that allows us to get back to our nominal voltages in those cavities within about 2 minutes, and sometimes a little bit faster. So we can turn the entire linac back on within about 2 minutes. And at the same time, we can take it down a little bit faster than that. So all of the cavities can be turned on and off in about 2 minutes. And so that allows us to introduce some efficiency back into the process for the users. They don't lose that much time. And honestly, that 2 minutes is about the amount of time it takes them to walk from the control room down to the entrance of the linac. So no time is necessarily wasted. This is kind of showing a study that we did over about 1 hour, where we actually introduced and turned on and off the SRF voltages on those cavities to the levels that we would need to support operations with different ion species. And so this was essentially, if we were to do this, is an exercise in how fast we can change the settings for the linac. So we can go through about 5 different beam settings within an hour, maybe even faster than that if we don't need to have operations go for as long as shown here. So that was a very successful um, process that we developed with cooperation of our SRF group and our RF controls group. Other improvements that we've been making is on those windows. So as I may have mentioned, the thickness of the windows that we use, these polyethylene naphthalate windows, the thickness that we started with was 100 microns. 100 microns thick, which for the heavier elements is a significant amount of energy loss going through the window. And we also started with a relatively small window, only 1 inch or about 25 millimeters in diameter. And so we've made a couple of improvements now. We've gone from a 100 to a 76 micron thickness. That the 76 was not available to us earlier, but it is now, and it's been tested and vetted. So it's a material thickness that we can use in this application. And we've also gone from a 1 inch to a 2 inch diameter. So for our next iteration of our window, well, it'll be slightly thinner, so we can reach some higher energies with the heavier ions, and a larger size, so we can at least start to grow the amount of area on a part that we can irradiate. We are also moving towards a 5-inch diameter window, kind of on our way to these larger windows with these thin materials. And so we are looking at using a titanium mesh, kind of shown here in this picture, as a material, a mechanical support material. Because at some point, the windows are just not going to be able to support themselves against atmospheric pressure to vacuum. So the titanium mesh is seen as a way to get us to larger sizes with the small material. There is, of course, going to be some interception of beam. There's going to be some scattering, some energy losses, and so that still needs to be quantified. But within the range of LET measurements and FSEE type of measurements, it should be a small effect. Okay. We have incorporated machine learning, essentially as a background R&D project for operating the SRF linac in general, and how quickly we can tune, which has benefits both for the nuclear physics program as well as for the radiation effects program. We've concentrated on models using Bayesian optimization as well as neural networks. And their combination to allow us to quickly tune the transport through the linac for these beams, so that we can tune essentially the transport and the emittance within just a few minutes. And so that greatly aids retuning the linac in case a cavity goes down or we have to retune around something. We also use these techniques now, neural network systems in particular, to help us look at the quadrupole term. That seems to be a pretty popular subject these days. So we use BPM related data from 4-button BPMs measurements to help reconstruct with these appropriate models and training of the agent to develop basically the quadrupole moment of the beam, and again that then feeds back into beam transport tuning. And quickly retuning the linac. In terms of new capabilities that we are developing, we're capitalizing on using a linac-based system, which can generate some tailored time structures as well as continuous and pulsed operations, and we're exploring these high flux modes. So let me talk about that for a few minutes. So the RF nature of the linac generates basically a series of these pulses. We have a 40.25 megahertz RF system for the beam. So the beams then appears as these peaks every 25 nanoseconds, and so that's our microstructure. That's just basic part of an RF linac. We incorporated electrostatic chopper in the front end near the ion source, which operates at a 100 hertz repetition rate, or essentially a 10 millisecond cycle. We have to incorporate a small gap in there for diagnostics, but then we have freedom to control that the rest of the 10 milliseconds. So Normally, we provide all of this beam, all essentially 10 milliseconds. So we provide a continuous beam to the users. But we can change that. We can go to smaller duty cycles, smaller pulse durations, all the way down to about a microsecond pulse duration. We can do single pulses or up to 100 hertz. And so that then allows us to explore different ways of delivering beams to users who may have slightly different needs. The whole front end system gets in on this. The ion sources are shown here. We use these dipoles and slits as our charge to mass filter or mass to charge filter. An electrostatic chopper is here in the front end, which then now defines the duty factor, the rep rate as well as the pulse duration for the beams as they are then injected into the accelerator and delivered to the experiment. So we can now use the concept of a chopped pulse. So going from a CW, continuous pulse every 100 every 10 milliseconds to something much shorter as a way of fine-tuning the flux that we deliver. So it's a very fast, very accurate way of making rough, large or fine scale adjustments to the average flux that we deliver. Of course, the peak flux is always the same. And so it really kind of depends if the user's device can withstand these short, high fluxes. But if they can, this provides a valuable knob and a very quick and easy way of tuning the flux to what the users may need. And we can do that now over 6 orders of magnitude pretty much instantaneously. Other capabilities with pulsed beams now. So I mentioned the average flux that we can deliver for any ion species, but that's the average flux. We can go to much higher fluxes over shorter amounts of time using this kind of basically pulse mode delivery and generate instantaneous fluxes up to 10 to the 12 ions per square centimeter per second, in a focused beam rather than a uniform beam. For uniform beams, we can generate fluxes up to about 10 to the 10 ions per square centimeter per second with appropriate duty factor limitations on the delivery so that we don't exceed that average flux or the average power onto the window. We currently measure using our standard instrumentation, which is bandwidth limited to 120 hertz bandwidth. So you get a little bit of you get a broadening effect, a filtering effect. But that's taken care of if we just are looking at the amount of charge generated by the integral here, as opposed to flux over the short pulse. So we now can do this. We can deliver a single pulse. We can deliver 10 pulses or 100 pulses or however many pulses the user might want in a particular chain of pulses. The pulse to pulse intensity or amplitude spread is very small. And so now we can use this to generate different types of time structures as a user may want or be interested in for their types of devices. This is just kind of showing an experiment we ran into, basically at short pulses, at small fluxes, we get into instrumentation noise effects. At longer pulses, at higher fluxes, we get into saturation effects on the instruments, and these are all understood, and we're pushing back on the saturation side now, and the noise side will incorporate additional mitigations. The last thing I want to just mention is we've had some users who are interested in neutron effects, and barring a high flux or the ability to look at a high flux or a pulsed high flux neutron source, there was some interest in looking at some correlation studies for utilizing heavy ion beams with the appropriate LET, the appropriate energy and mass, which can simulate in kind of an analog beam sense the interaction of neutrons with, say, silicon, the generation of recoil products, which then deposit energy into the electronics itself. And so this was an interesting set of tests that we did with some folks from Sandia National Laboratories, where we used a 40 argon beam to simulate a 14 MeV neutron. So this is kind of an interesting way of utilizing heavy ions as a substitute for neutrons to essentially put brackets or limits, upper or lower limits on the cross section on the effects that the electronics might see. So finally, in terms of where we're going now, I mentioned that we started with a K500 driving a K1200 cyclotron. The K500 is still there. We are now developing a standalone SEE beamline based on a K500 cyclotron, plus a delivery beamline and a user vault and user station. This has now been built. We are now commissioning it. And we are also building an extension to this building to host an additional 3 test vaults, or to bring us up to a total of 3 test vaults. Again, kind of showing a similar type of beamline structure that you might expect. So we're expecting now first operation in July. So we're almost ready for users to come and visit the station. And again, it'll be dedicated, so we don't share the linac with the nuclear physics program like we do with the FSEE beamline. And then finally, we're working on some higher energy beam capabilities. First one is just developing another beamline, but attached to the high energy linac side in the same tunnel. That'll get us to energies above 150 MeV per nucleon for our bismuth, and then of course higher for the lighter species. And we're also developing plans and talking with various funding agencies to develop essentially a light version or a reduced scope version of the entire FRIB linac as a greenfield facility to get us into the kind of the 350 MeV per U regime, again for the heavier ions. So those are our projects. That's our work right now. We're entering into our 3rd year of operation on the linac-based facility, where we're providing up to 2,000 hours per year that we share with the nuclear physics program. We're beginning our user operations for the K500 facility next month. And we have these projects for higher energy beam delivery that we're pursuing. So thank you all for your attention, and I'm here for any questions.